All right, so we are looking at chapter 10, 10, which is hypothesis testing. And today we're going to talk about the results step. For this results step, what we're looking at is how does our sample compare to the common view? And remember that common view is our null hypothesis. So that's what we're looking at. So the way I'm going to look at this today is we're going to take a look at this in the numerical variable and then for the categorical variable. So remember, if we're looking at numerical data, we are studying mu for the means. And when we're studying mu, we are on the t-curve. And when we're on the t-curve, we have degrees of freedom equal to n minus 1. So the first thing under our results step, what we're going to do is we're going to calculate what we call the t-test statistic. Okay, so our t-test stat value is equal to our sample mean minus our center of our curve divided by the spread of our curve. So this calculation should look really familiar to us because if we look at this, we can see that this looks very similar to the z-score calculation, right? So we're taking our value minus the mean divided by the standard error. When we did it z-scores, it was our data value minus the mean divided by the standard deviation, right? So it's very similar. It has the same meaning. So this is the number of standard errors away from the center. And our center is this mu naught value. So remember how when we're calculating normality for categorical data, I introduced this value P naught. That's very similar to mu naught. Mu naught is just for the numerical side. So this is the value from the null hypothesis. It is the center of the curve. So mu naught similar to P naught in the fact that it's from the null, it's the common view, it's the center of our curve. And I also want to mention here our standard error, how we calculate that. Standard error is just S divided by square root of n, so nothing new there, but I just wanted to remind us of that. So this calculation is very quick because you can see all we're doing is subtracting, then dividing. And I will, of course, give you steps on how the calculator will do this calculation for us, although it's fairly quick. And now we need to interpret this value. So we need to put it into words, which I already did right here for you, right? It's the number of standard errors away from the center. So we're just going to write that out. So for this numerical data, we need to now interpret this t-test stat value. So I'm going to give you a template. You may use the template. You may rewrite it in a different way if you want. But just so you know, when we interpret these numbers, just putting them into words, you can use the template I give you. So I'm going to say our X bar, or if you want to say our sample mean, that'd be good too. So whichever one, you don't have to write them both, is whatever our value is, our test statistic. So it's the absolute value of the t-test statistic standard errors now. I've got two more blanks here. It's going to be above or below. Above meaning my test statistic is positive. Below would mean my test statistic is a negative value, which we'll know because we calculated it first. And it's above or below our center, which is our mu naught value. So I'm going to put center. So when we go through an example, you'll see I'm just actually going to put the value here. So if the center is 5, I would put 5. Okay. So I just took the meaning and just wrote it out. You can always use this template if you want. Okay. Keep in mind, this is for numerical sample mean. If it was proportions, it would say sample proportion or p hat there. Okay. So now the third part, we need to do another calculation. And here we're going to calculate the probability of a t value being less than or greater than. And you know, you can always have the equals under there. It doesn't matter in stats. It's kind of all the same. No, it's not in calculus, but in stats it is our t value. So let me write it like this. So we got it here. Our t-test stat value. So we know that's exactly what we're looking at. So we want to calculate the probability of another t value being either less than or greater than. We'll know which one it is. We'll look at the picture. Then our test statistic, the one we got up above here. Okay. This is called the p-value. So I'm really sorry for this. So you know how we have in proportions, we have p, p hat, p naught, probability. Now I'm going to introduce another word starting with p, which is p-value. P-value represents this probability that we're going to calculate here. Okay, that's what we're doing. Now, this is something a little new for us because we're on the t-curve, right? We haven't done this. So on the t-curve, we're actually going to calculate using what we call the TCDF. Okay, so the T cumulative distribution function. So it's very similar to the normal CDF, but now I'm saying, okay, I'm on the T curve. So we can find this on our calculators or Minitab. When we're calculating on the T, for the TCDF, this probability, just like before, I'm going to put in my lower bound. So just like before, like I'm saying, if you use normal, my upper bound, and keep in mind, I'm on the T curve. The T curve is centered at 0, right? So the T curve doesn't depend on the center here, but I need to put in degrees of freedom, which equals n-1. Remember, the T curve depends on that, so I need to put that in. You'll see when we work through an example exactly what we're going to plug in there. It's just n-1. So I want to draw you a couple pictures so you can get a visual of what's going on, okay? So for this visual here, we have the 3 different scenarios, right? Sorry about my drawings today. They're out of sorts. It's hit or miss. Some days they're better than others. Today they're not great. So we have 3 different scenarios. So we have this scenario where we have this like left tail, right? And we're calculating the area over here on the left, okay? Or we have this scenario where it's right-tailed and we're calculating the area over here, right? That's what this probability is doing. Calculating that area. Or we have what we call two-tailed. We haven't really looked at this yet. I haven't thrown this at you yet. I will shortly. And a two-tailed means I have two tails. So it means it's symmetric. And what happens is when we're looking at these, the p-value is this area. Okay, so this equals the p-value. And right here, the area equals the p-value. And that's what we're calculating up here, right? Now, when I calculate on a two-tail, this just means it's a not equals for my null, or my alternative hypothesis. So here I have a p-value, but I don't need just one, I need both. So in this scenario, what we're going to do is we're going to multiply the p-value by 2. So we can get the area in both tails. So our calculator will only give us the one tail. We need to multiply by 2 so we get the total area in the tail. Okay, so we'll keep that in mind when we see that come up. But that's what the p-value is. It's the area in our tails here. Okay, I like to give you that visual. So now what we need to do, once we get this p-value, we need to interpret the p-value. So we need to interpret the probability. So what that means to us. So that's the fourth part of this step. So we're going to interpret the p-value. So I'm going to give you a blanket interpretation, meaning just like a template statement, and you may always use that, or you can write it in a different way if you wish. So I'm going to write it out and we'll discuss it. So if the population mean, right, because we're talking about numerical data right here, equals our center of our curve, which for us is mu naught right here. Right? There is a p-value. I'm going to plug in p-value right here. Probability of getting a sample mean at least as extreme as the one we got from sampling. So let me explain this to you because this can be overwhelming, this interpretation. So what we're saying here is that if the center of the curve is my null, my mu naught, okay, then the probability we calculated up here, the p-value, is the probability, okay, of getting another sample mean. So maybe a second sample mean. Now it says at least as extreme as the one we got originally. So what it's saying is that this value right here, this area in the tail right here, is the probability that we're going to get a second sample mean this far away. That's what the at least as extreme as, this far away from the center as the original. So this red line is the original. So that's the one we got. This is my X bar, okay? This would be my X bar, okay? So it's just saying that this is the probability of getting a second sample mean that far away from the center. That's all this is saying. Okay, that's the p-value that we're calculating. So the idea is that, and I'm just going to say it and we're going to talk about it more next week, but the idea is if this is so far away from the center and I have this really small probability of getting another one that far away from the center, then maybe the center shouldn't really be the center. Maybe mu naught really shouldn't be the center of my curve. That's the idea. Don't worry about it right now. We're going to get into that more, like I said, next week. So that's the 4 parts to this next step, okay? 2 calculations, 2 interpretations. That's for the numerical side. Let's take a look at the categorical side. It's really similar. It's just little things like mean. Right here would be proportion, right? And this would be p naught. So it's stuff like that that changes based on the type of data. So there's really not a big difference. It's just little things. So we'll take a look at this. So categorical data, and keep in mind this is for p proportions. So remember, if we're looking at categorical data, we are on the z-curve. So we're going to calculate first the z-test statistic. Okay, so z is equal to p hat minus p naught divided by the standard error. I want you to keep in mind this has the same meaning as it did for numerical. My z-test statistic is still the number of standard errors away from the center. It's just now my center is p naught. So what it's saying is this is how many standard errors away from the center my sample proportion is. So it's telling me how far my p hat is from the center based on my standard error. Keep in mind here, standard error, remember for proportions, is the square root of p times 1 minus p divided by n, right? But it's not p in this calculation. Think back to last week when we were checking normality for proportions. We use the center of our curve. Same thing for the standard error. We use the center of our curve. The center of our curve here is p naught. Remember, that is the value from my null, okay? So this is the value from h naught, center of the curve. I know we already know that because we talked about it last week, but I still am going to write it. Okay, so now the next thing after we calculate the z-test statistic, I want to interpret this. So to interpret it, it's the same as the numerical side. So when we interpret this, we can just say our p hat, or you could say sample proportion. Is whatever this value is for my z-test statistic. And the absolute value, standard errors above or below. Above, again, meaning it's positive, below, meaning it's negative, my center, which is p naught. Okay. So that's my interpretation. So you'll notice it's exactly the same thing as the numerical, except for I use p hat or proportion, and the center is not mu naught, it's p naught. Okay, so very similar. Now I'm going to look through and calculate the probability. So I'm going to calculate the p-value. And to calculate the p-value, I'm looking at the probability that a z is less than or greater than the z-test statistic I already have. Okay, so that's what I'm going to do. So here I'm going to use what we've used before, normal CDF. And when I'm looking at normal CDF, I'm going to enter in that lower bound, upper bound, and then my center and my spread. But let's take a look. It's the probability of Z. I'm calculating the probability of Z. What do you think my center and spread should be if it's the probability of a Z? Think about it. On my standard normal curve, my center is 0 and my spread is 1. Okay, probability of Z. And on my standard normal curve. That's what the z-test statistic does. It's just like the z-score. It standardizes it. It brings it down to a curve with a center of 0, spread of 1. Okay, so here my p-value is going to represent that probability of getting another sample proportion as far away from the center as my original one. Okay, so I'm going to do the same interpretation. As numerical. Okay, so interpret the p-values here. So now I'm going to say if the population, now it's proportions, right? So proportion equals p naught. There is a p-value probability of getting a sample proportion. So I'm talking about categorical. At least as extreme as the one we got from sampling. So it's the same interpretation as numerical, right? It's the same meaning. My p-value still means the same thing. It's just now I'm talking about categorical data. So it's just saying if my population proportion is p naught, right? So if that is truly the center of my curve, then the probability that I just calculated up here is the probability of getting another sample proportion. So taking another sample and getting a sample proportion that far away from the center as I got from the first one, okay? Or even further away. That's what the interpretation's saying. Okay. So guys, let's apply this to those examples that we started last week. So we have 2 examples. I'd like to walk through these both. So, so let's look at the same example as last week. And the first one we looked at were the students and if they approve of the admin. Okay, so we're looking if students approve the admin. So let's recall some information because let's face it, it was last week. So let's recall what the null hypothesis and the alternative was and some sample information so we can apply all of this. So my alternative, if we remember, the professor wanted to prove to the community that the proportion of students on RIT campus that approve of of the university admin is greater than 67%. So we have greater than 0.67. So that makes the null P is less than or equal to 0.67. Just keep in mind, 0.67 is the center of my curve. I'm actually going to draw it out because I think it's really helpful to see. This is why all the time I say to you guys, draw it out. You don't have to show me, but at least draw it out. So this is 0.67, right? Okay, and from the sample piece of this, we got, let's see, X is equal to 62. N is equal to 80. Then we found P hat, we calculated it, which is X over N. So it's 62 divided by 80. I know we already did all this, 0.775. I'm just refreshing our memory. And we did check for normal, and this one did come out normal. So we can move forward. That's what that's meaning. So what we're looking at is over here, we have 0.775, right? And we want to calculate this probability to the right of 0.775. So for our results step, I need to calculate Z first. So I need to find the Z test statistic. So for my Z-test statistic, I'm using the calculation of my sample proportion minus the center divided by the spread. I'm actually going to write the formula right in here. So P naught 1 minus P naught divided by N. I'm just going to plug all the values in. P hat we found is 0.775 minus P naught, that's my center from my null, that's 0.67. And my standard error uses that center to calculate the spread. So here it is, 0.67 times 1 minus 0.67 divided by N, which is 80 all under the square root. So I just broke this out into numerator and denominator. I found 0.105 for my numerator, and my denominator is 0.0526. So I ended up getting a Z-test statistic equal to 1.9973. Now, yes, I could have rounded that to 2, but I don't like to round so early because I'm going to calculate a probability up here. So I don't want to round it too early. Now, I just want to give you the visual of what's going on here. So this is my curve for my data, right? My sample proportion. Here's my P naught, the center of my curve. What does 1.9973 have to do with it? Well, now I'm bringing this down onto the Z curve. The center of the curve is now 0. My P hat is now my Z test statistic, which is 1.9973. Do you see that? Can that give you a good visual? I've now removed this axis and I've replaced it with a Z axis. Okay? And we're still going to calculate that area in the tail. So hopefully that gives you a good visual. So I'd like you guys to draw it out. All right, so here's my Z test stat. So now I need to interpret this. So interpret the Z test statistic. And that's just saying that my sample proportion is this many standard errors away from the center. So I'm going to say our P hat, I'm going to kind of shorten it. Our P hat is 1.9973 standard errors. It's positive, right? It's a positive number above my center of 0.67. So it's like a quick little statement. Okay. It's just telling me how far away my 0.775 is when we're looking at standard errors from the center. Professor? Yeah.
So if when we did that calculation of the Z-test statistic all the way to the end, like where we have like 0.105 over like 0.05 526. If that came out negative, will we then say our p hat is like negative whatever number standard deviations below like our center point?
So you would still use absolute values. So if this was a negative number, you would say our p hat is 1.9973 standard errors below 0.67.
Okay, so we just switch
So
out
yeah,
above or below.
you're thinking about it the right way, and it would be down here.
Okay, I just want to make sure we'd still like word it the same way when we interpret.
You would still word it the
like
same way. You would
make
still
sense.
write the positive number here and just say below. Yep, you're right. Okay, so let's move on to the second two parts, right? So those are the first two parts of this step. So the next thing is we need to calculate that p-value. So I'm gonna leave this up on the screen. Hopefully we can see. So the next thing we wanna do is we wanna calculate the probability of another z-value, okay? And we wanna compare it to this 1.9973. So I need to take a look at my picture. Because remember before, when I was talking to you about it, I said it's going to be either less than or greater than. So how do I know which one it is? Well, first of all, it's going to match your HA. Okay, first of all, it's going to match your HA. So your HA is greater than, this will be greater than. But let's take a look at the picture to see why it's greater than. This is what we're doing. We're calculating the red right here, right? We're going to calculate this area and the tail on the right. I want to know what the probability is that it's greater than this test statistic of 1.9973, right? Greater than the sample proportion of 0.775. Does that make sense? So this is a greater than here. And when I have that visual, maybe I'll just show it to you like that. When we have that visual, it helps us figure out the lower and upper bounds, right? I mean, this is something we've done before. This is not new. So here, I'm going to take, since it's a Z, my normal CDF calculator or Minitab function, right? My lower bound here, now remember I'm on my Z curve, so it's the 1.9973. I'm not using p hat anymore because I've switched to the Z, right? It's probability of Z. My upper bound is going to be that positive infinity. You know I'm not going to plug infinity into my calculator, but when I write it out, that's what I use, my infinity. I'm going to use something like positive 10,000. The center of the curve is 0, and the spread of the curve is 1. So now this will be my p-value. It's my probability. So p-value here, when I plug all this in, I get 0.0229, or 2.29%. Okay? So that's my p-value. Now I need to take that p-value and I need to interpret this. So we need to interpret the p-value. So again, it's like that statement, and you can use the same statement. So if since we're talking about Z proportions, it's a population proportion equals, or you could say is, so if that is the center, so if the center of the curve is my null, my 0.67, then there is a 0.0229 probability. I just took my calculation from here, plugged in, probability of getting another sample proportion. So a sample proportion at least as extreme as the one we got from our original sample. So this is just saying that there is a 2.29% probability of getting another value, another sample proportion out here in the red, this far from the center. So at least as extreme as. So this far or the same distance from the center. That's what that's saying. Based on that the center is 0.67, right? My calculation for my Z-test statistic was based on the center being that 0.67. So that's why we state that here. Okay, those are the 4 parts to my 4th step of my hypothesis test. Okay. All right, let's take a look at the second example that we studied last week. So this example from last week, this is the apples example from last week. So again, let's recall some information and just remember a little bit because it was last week. And it's hard to remember stuff. We've got so much going on. So my null and my alternative, remember the alternative is what the manager was trying to prove, and that was that the mean weight is actually less than 6 ounces. So that means that's the alternative. So that means the null is greater than or equal to 6 ounces. We're on the T curve because it's numerical, it's means. So from the sample, we gathered that the sample size was 61. The sample mean was 5.6. The sample standard deviation is 0.1. And we did check it is normal because N is greater than or equal to 30. So let's take a look at the result step. So that's all stuff from last week, right? That's nothing new. We gathered that last week. So my result step, I need to calculate the t-test statistic. And that's going to be the sample mean minus the center of my curve, which is mu naught, divided by the standard error. So I'm going to fill in with the calculation here, s divided by square root of n. So let's plug in these values. So I have 5.6 minus 6, right? 6 is my mu naught, that's from my null, divided by this sample standard deviation of 0.1, and that's divided by the square root of n, which is 61. So when I get this calculation, I actually find the answer to this to be negative 31.24. This is really far from the center. Negative 31, think about it, a z-score. So think back just to z-scores and like the common idea. Anything outside of 2 standard deviations from the center is unusual, right? An outlier. This is negative 31. That's how far it is. So keep in mind, it's the same idea as all the other stuff we've been talking about previous lectures. This is far. So now I'm going to interpret this value. So when I interpret this t-test statistic, I'm just going to simply state that our x bar is 31.24 standard errors below the center of 6. Okay, so it's pretty far. Okay, let's move on to calculating the p-value. So my p-value is equal to the probability of getting another t, right? And I know it's going to be compared to this negative 31.24. So let's visualize this. Let's see what's going on. So let's draw a picture here. So my center is 6, right? And my x bar was 5.6. So what that means on my z curve, my t curve, I apologize for that. My t curve, that means that this value right here is negative 31.24. And my center is 0. Okay, so that's my visual. So what I'm doing here is I'm calculating this area to the left. Like I'm not going to calculate all of this to the right. It's always the smaller. Remember what I said, it matches my HA, less than. So this is going to be a less than. You can write less than or equal to. It doesn't change your calculation any. So here it's T, so I'm going to use TCDF. So the T cumulative distribution function. you can find that in the same place as you'll find normal CDF on your calculators or on Minitab. So TCDF, remember what I mentioned before, we're going to put our lower bound. Our lower bound here is negative infinity, right? And then our upper bound is this negative 31.24. Oh, I didn't mean to put that in there. And then I'm going to put my degrees of freedom. So degrees of freedom is n minus 1, so I will put in 60 here. So just keep in mind, this is degrees of freedom equal n minus 1, just because that's new for us. Just wanted to write that down, okay? All right, so we get the p-value. Now, it should be really small, right? Because that many standard errors away from our center is really far away. So our p-value on our calculators or Minitab is going to come out as 0. We never use 0. We never say the probability of something is 0 because 0 means there's no chance of it happening. And there is a chance of it happening. It's just very small. So instead of 0, we say very small. Okay, so we're always going to say very small. So instead of saying 0, I'm going to say my p-value equals very small. That's what I say. I never report it as 0. And now I need to interpret this value. So to interpret my p-value, I'm going to say if the population, now we're talking about numerical data, right? So it's mean, equals 6, right? That's my null. So if the center is 6, there is a very small probability of getting a sample mean that's numerical at least as extreme as the one we got from sampling. So it's just saying that there's a really small probability of getting a second sample mean that far away from the center. That's what that's saying. Just show you guys that for just a minute. So guys, you know I'm always going to upload these online. I know this was longer, it was like 8 pages of notes that I had handwritten. That's funny because my handwritten notes are only 2 pages. So let me switch this around.